using spin motion rather than charge motion. By the way, this is the semiconductor chip, and I started my career as a circuit designer right after my bachelor degree. And 20 years ago, this was 50 megahertz, state-of-the-art technology at that time. But now you look at your CPU in your computer, it's like 3 gigahertz. So you can see about 100 times, enhancement in terms of speed. So what will happen after 20 years from now on? What will be the speed? Or, is it possible for us to move, 3 gigahertz to 300 gigahertz in 20 years? How do you think? I think it's very challenging. And a lot of people in CMOS, often talk about we already reach the limit of, the radar scaling. So that's why I think this spintronics offer kind of a new direction, what we can do, using spin information. So if you look at this individual transistor and interconnect, we consume a lot of energy due to charging and discharging of electrons. And we want to move to, for example, spin transistors or interconnect we can replace by spin waves. Is it possible? I think it's a very interesting research area. On the other hand, this magnetic tunnel junction based magnetic random access memory was already commercialized. You can buy it from Everspin. 2 months ago, Samsung also announced mass production and they shipped to Sony, which I'm going to introduce later on. So if you look at this MRAM die, and most of these random access memory use cross-point architecture, so-called, and then you can see word line and B line crossing each other. At the junction, you have 1 bit of cell. And once we amplify those 1 bit, it's a sandwich structure, so-called magnetic tunnel junction. So we have 2 magnetic layers. In the middle, we have insulator. Mostly these days, we use magnesium oxide because of the spin filtering effect. If 2 magnetic layers are pointing same direction, we have high current. One of the layer flipped. This is called the anti-parallel configuration. We have low current. So we can constitute digital information 0 and 1. So this is a foundation how we can store, basically 0 and 1. So what will be the future direction of this magnetic tunnel junction based applications? We can replace eFlash in smart card, or even we can imagine, SRAM replacement, so-called L3 cache. So basically this is a CPU memory. But we want to replace those using a non-volatile, even wearable. You can see a lot of applications, biocompatible in the future, and so on. So my group, we've been trying to understand what is the strain effect in this magnetic tunnel junction last quite a number of years. So first we use diamond-like carbon. So this is called DLC. And this is a very interesting and important material in hard disk drives. I'm pretty sure later in this afternoon, you will learn about this material. Then we incorporate this material on top of our MTJ. And this material is known to have a very compressive strain, right? So you can basically push, your MTJs in retro direction. And what we found is this TMR value is quenched once we put this DLC on top of our device. So this was rather discouraging because we always want to improve TMR, but this one in fact reduced TMR. Then naively we thought, if we can somehow give a tensile strain, if we can stretch out, probably we can improve the TMR. And then I talked to many material scientists. Do you know any materials we can, give a tensile stress? And I was found it's not very easy. So then we made, university types of, crude mechanical stage. You have a sort of rotation stage, and this bullet will move up and down depending on rotation. Then we put our wafer there, and then you can basically give mechanical, stress there. So once you have your magnetic tunnel junction on top of this wafer, basically you can sort of stretch out. Then we rotate this screw as a function of fine angle. Then we found the magnetic tunnel junction TMR value can enhance from 120% even up to 260%, and is quite repeatable. So this really shows possibility we can give a tensile stress, then we can improve TMR. So that really confirmed our initial idea. So recently we tried to make fully flexible MTJs, and initially we tried to deposit on top of piezo substrate or plastic substrate. All failed because most of the real materials are very rough. Then recently, discovered this MGO requires only 1 nanometer, a very flat layer. So it's not very easy, to deposit directly on a very rough surface. So we just deposit on a conventional silicon wafer, then we can etch out the handling wafer. Then those MTJ will be very thin, suspended layer. Then using a stamping technique, using PDMS, this is just the typical, your rubber eraser. You can just attach and then move to any foreign substrate, like this is a plastic substrate. So during this process, if you look at the lattice constant, there is an interesting behavior. If you look at this initial lattice of MTJ and then final one, you notice there is stress on the lateral direction. This is due to the compressive strain initially given by this silicon oxide. Silicon oxide, people typically think this is amorphous and probably no stress, but in fact it's not. It actually gives a compressive stress. But once you release your underlying silicon substrate, then this silicon oxide can be stretched laterally, and then eventually your MTJ can be also stretched to laterally. So then we can see interesting effect. Once we have a tensile stress, we expect enhancement of TMR. So in fact, this was observed. If you look at on top of a silicon, we have a black curve as a function of TMR and magnetic field. But as soon as we move this guy on a plastic substrate, you can see the TMR improved immediately. And then also the loop response became much square. This square behavior is known as a magnetostriction. So once you have magnetic domain and you stretch, what happened? Your magnetic domain aligned better in one direction, then your magnetic response will be more abrupt. So that's what happened, this very abrupt response. But the enhancement of TMR cannot be understood using this conventional magnetostriction theory. So we tried to understand what is going on. We had a collaboration with Professor Mark Sayes in Ghent. So he did the K-resolved transmission calculation. So basically this is a quantum mechanical transmission probability calculation. In parallel alignment, when two magnetic electrodes are pointing same direction, there is not much change regardless of tensile or compressive strain. This is a particular feature of MGO. This tunnel barrier is very robust against in any disturbance in case of parallel alignment, not like aluminum oxide. But if you now make anti-parallel alignment, so you flip one of the magnetic electrode, and then we apply different types of stress, and you can see from the initial configuration, once we give a tensile stress, the transmission probability decrease. So if we have a less transmission, basically the resistance of anti-parallel will increase. Then your TMR will increase eventually. So in case of a tensile, basically we will increase TMR, but in case of compressive strain, we will decrease the TMR. So this is the underlying principle, how we can give a sort of strain engineering in magnetic tunnel junction. We can in fact move this array of MTJs to any foreign substrate. This is example of glass. You can see many arrays of MTJs. It's difficult to see. This is aluminum foil, PDMS, nitrogen glove. Recently, my student, was able to move even on our cloth or paper and no restriction. And once we move, this is example of aluminum foil. We can measure the TMR very carefully because you can easily punch through this whole structure with your probe station needle. And you can see the TMR response is more than 220% and very square response and so on. So the junction property is maintained without any degradation. So I hope this gives some kind of proof of concept. The magnetic tunnel junction or even MTJ-based sensors can be applicable, wearable, or flexible electronics applications in the future. So once we have this very established MTJs, now industry people can make much better than typical university laboratory. That's how they commercialize this technology. So initially, this magnetic random access memory was released by Everspin using toggle RAM. So this is no more than simple magnetic field-based switching. So you have to apply large charge current and generate the fringing field to switch your information storage free layer. And then later on, people spend quite the time to understand this spin transfer torque phenomena, in which we can just inject charge current into the junction, and depending on the charge current, you can switch one to the other layer. So as you can see, the structure architecture is very simplified compared to this field-based switching. So that's why all the major companies are now investigating, how to commercialize this STT technology. And last year, IBM announced Everspin-based STT MRAM on top of their flash core module, so they can improve the system performance. Last few years, also Everspin with the global foundry in Singapore, they produces sampling chips and ship to many system integration companies. And 2 months ago, Samsung mass-produced this 28 nanometer based embedded MRAM. Then they shipped to some customers in Japan. So I think now we start to see more and more real application using this STT MRAM. And as time goes, I expect more and more, consumer electronics will come, and we will enjoy some kind of boost in system performance and probably new experience even. So as academia, we have to think about now what will be the future direction of this MRAM, how we can improve, or what can we do. So nowadays, probably you heard about a lot about this spin orbit torque MRAM. So that's one of the topics I'm going to introduce today. So as Professor Lee explained what is spin orbit coupling, probably I don't need to show, but typically this is the slide I want to show to the first year graduate students, to easily understand. If you have a rotation ball, okay, and then initially this ball is moving in this direction, but if you look at the relative velocity at this point and this point, you have a different relative velocity because of spinning, and this ball will deflect in this direction because of this rotation. If you rotate in opposite direction, this ball will move to the other direction. So this is basically the deflection can be considered as spin current, and the initial ball motion is charge current, and the rotation axis can be considered as spin polarization direction. For example, if you rotate this ball in this way, then the rotation axis is in parallel with this initial ball motion direction. Then what will happen? This ball will not deflect. It will move straight because the spin polarization and charge current direction is in parallel. So as Professor Lee explained, these all three components should be orthogonal each other to see this interesting behavior. So exactly same thing happen in a solid. If you have a spin polarization, electrons will deflect in one to the other depending on spin polarization direction. So this behavior first discussed by Professor Diagonov in 1971, and like a typical big discovery, nobody paid attention for a long time until 1999, and Hirsch sort of revisited about this phenomena, and then extensively discussed by many other scientists and engineers. Experimentally, Ganichov in 2002 showed the spin galvanic effect, so in which he shined circular polarized light in gallium arsenide and measure charge current. In a metal, Vanezuela and Saito used the inverse spin-Hall effect in platinum. So then they inject the spin current and measure charge current. So that is basically the history of this field. So depending on the origin, we typically discuss into two major phenomena. One is a spin-Hall effect. As previous speaker explained, this is coming from Burke and typically quantified by this theta, which is a proportional constant between the injected charge current and the spin current. So obviously, we want to have a larger value in this theta. The other one is a Lashiba-Edelstein effect. It's coming from the broken symmetry interfacial effect. So the easy way to understand this at the interface, once you have a semiconductor and metal, you have electric field due to work function difference. Then the moving electron feels this electric field as if magnetic field. So this effective magnetic field can give you basically the polarized spin accumulation. So that's a very simple way to understand this phenomena. But in reality, what happened? If you look at this structure, we always have underlying substrate. So then you have substrate and your material, and you will have interface. If you have interface, you have this phenomena. Now, if you look at the top, your sample has a vacuum interface. So then you also have some kind of Lashba effect here. So in reality, it's not easy to distinguish in real material system. Always sort of coexist. And scientifically, of course, is interesting to distinguish how much percentage is coming from this, how much percentage is coming from this, whether those two guys have the same direction, same sign, or opposite sign. So I think those are all very interesting topic, I think for you guys can study. So imaging is believing, as he also introduced this Santa Barbara show, very beautiful imaging depending on the spin direction, and indeed, up spin and down spin separated in both edges, and we can see those. This measurement is very easy to repeat in semiconductor, but it's very difficult to repeat in a metal. And in fact, nobody showed this image in a metal because the background, carrier density is so much in a metal. So even though you generate extra spin polarized carriers, it's not easy to measure those delta. So we try to make a new setup called the scanning photovoltaic microscope. So we pattern as a kind of whole bar structure, and we can shine circular polarized lights, right hand, left hand, and typical magnetic material has a so-called magnetic circular dichroism. Depending on polarization, the amount of absorption is different. And we can define the photovoltage in longitudinal direction. If the material is not spin polarized, basically the right hand, left hand, polarized light will be absorbed equal amount. So this photovoltage will be 0. But if there is any preferred spin polarization, basically the absorption will be spin dependent or polarization dependent. Then either we will have a positive or negative this voltage. So depending on the voltage sign, we can determine what is the local spin accumulation direction. So this is the principle. Then we have a piezo sample stage, and you can move around, and eventually you can make a two-dimensional mapping. So we apply this one into a very well-known metal like platinum. So this is a top view from the channel, and you apply 0 current. Obviously, nothing should happen because there's no charge current, there's no spin current. Then we increase the amount of charge current, 3 milliamps. You can see a little bit some, bluish and the reddish. 6 milliamp, you can see very clear blue and red, which indicate down and up spin accumulated in opposite interface. Once we flip the current direction, exactly the spin accumulation flip the sign. So you can see red and blue. We can also use in a semiconductor. This is a bismuth selenide. Nowadays, people call it as a topological insulator, but it's simply a low band gap semiconductor. 0 charge current, nothing happens. And you can see 1 milliamps, blue and red, and -1 and red and blue. So it flips. So exactly, this is current-induced phenomena because the intensity proportional with the current, and then also the sign change depending on the current direction. And this technique is applicable in both semiconductor and metal. And especially in metal, it's not very easy to get those images, but this technique seems to be more sensitive compared to the conventional magneto-optical curve imaging technique. And this is also intrinsic measurement with only single material. You don't have to have a ferromagnet. So typically, you have to have a bilayer and measure torque. Okay? But in this case, you have a single material you develop in a laboratory, you deposit some interesting material. You want to know whether my material can generate spin current. Then you just need to shine polarized light and subtract the voltage. So this is, I think, relatively easy and more intuitive measurement. But of course, once you have this spin accumulation, we want to utilize those. Then we attach ferromagnet on top, and we want to manipulate those. And of course, the underlying principle could be either a bulk spin Hall or interfacial Lashba effect. But again, it's not very easy to distinguish. And the first seminar work was demonstrated by Mihai and Pietro Gambardella in 2011. So they use a cobalt platinum bilayer. Once you flow charge current in platinum, you can switch cobalt from top to bottom or bottom to top, depending on charge current direction. But in this case, because your accumulated spin in the middle of the channel is in plane, orthogonal to the current direction. Basically, typically we call this is Y spin. So your perpendicular spin, is orthogonal to each other. So you have to break the symmetry. So you have to apply external magnetic field to have a deterministic switching. So that is one of the limitations in current spin orbital engineering field. In order to switch PMA, we have to have external magnetic field. And obviously, this is a bottleneck for real application. And followed by the Cornell work in 2012, they used tantalum and the copper ion boron, and they were able to show a switching from left to right or right to left, depending on the current direction. But in this case, the accumulated spin is co-linear with the magnetization direction of copper ion boron. So you don't need to have an external field. But obviously, for nowadays application, everything moved toward a perpendicular system. Hard disk first, then even MRAM is all now utilizing perpendicular magnetic anisotropy. So this geometry is preferred, but you need the external field. So how do we quantify then the torque experienced by a ferromagnet? One of the established methods is so-called second harmonic technique. It's first proposed by, in this paper from Samsung, Dr. P. Then later in 2013, 3 groups developed more refined measurement independently. My group used more larger field measurements, so you can even extract the anisotropy field and so on. And the other group focused the small field linear regime, and you can fit those, and we can extract the effective magnetic field, coming from this spin orbital. The other quantity also we want to know is this spinor angle. This is all effective number because what you are measuring is sort of all entangled number. And the effective spinor angle is by definition the spin conductivity in this vertical direction divided by charge conductivity injected into device. But if you write down the spin current over charge current, we have very interesting enhancement factor L over T multiplied by spinor angle. L is device length and T is device thickness. And typically L is much larger than T in our modern geometry. So eventually your spin current over charge current, the ratio can be quite large because of this enhancement factor. And this can be understood as a lateral scattering idea. Once you inject one electron, this electron can give a torque, but there is no electromotive force in the vertical dimension. So this electron cannot go forever. It should come back and then it can give a torque again. So you can have a multiple sort of scattering at this interface. So it can generate multiple torques. But on the other hand, if you look at the conventional STT, you injected the electron, can be utilized only one time and then it should exit to the electrode. So this is vertical geometry, has a limitation in terms of the electron sort of scattering. And those two components, effective spinor angle and the SOT effective field, has some kind of linear relationship. So again, the bottom line is we want to increase those guys' number as much as possible because that will eliminate, decrease the switching current eventually. How do we quantify this spinor angle? The established method is spin torque ferromagnetic resonance. So on top of conventional FMR, we have additional these 2 torque terms. One is longitudinal and the other one is transverse torque terms due to SOT. Then once you measure the DC rectification voltage as a function of magnetic field, you have those, the rectified DC voltage, then we can decompose into symmetric and anti-symmetric component. And basically the intensity of those two can be compared, and then you can extract the spinor angle value. The other quick way to estimate the spinor angle is just look at current induced switching. So in a conventional Hall bar, we can induce the charge current and switch one of the perpendicular magnet on top, and we measure anomalous Hall voltage to look at the switching. This is one of the example of with the platinum. You can see clockwise switching with switching current with about 1 milliamps. In case of tantalum, you can see anti-clockwise switching, and switching current is 0.2. So obviously, you can now see, the sign is opposite because the effective spinor angle have opposite signs in platinum and tantalum. But also you can see the switching current is much smaller in case of tantalum, because the switching current and spin-or angle, there is roughly inverse relationship. So if you have a large effective spin-or angle, you can decrease switching current. So that's why we want to increase this number as much as possible. So effectively, this can be considered the effective spin polarization in conventional STT concept. So once we summarize this spin orbital engineering, we can decompose into 3 active layers. The first layer is a generation of spin current. Obviously, we always want to use heavy metals. Nowadays, people start to notice the interfacial effect is getting more and more important. And I'm going to introduce you some interesting materials, such as topological materials or 2-dimensional electron gas. So once we generate, now we have to absorb this spin current. Obviously, the first choice is ferromagnet, because we know how to make it, how to detect and utilize. Nowadays, you probably heard a lot of anti-ferromagnet based research work because of small fringing field, very high thermal stability, and so on. But it's not very easy to detect because the moment is negligible, and also it's not easy to fabricate. So I'm going to introduce some concept of multi-layer and ferromagnet in my talk. Then the capping was largely ignored. And typically people thought, we have this 2 functional bilayer, but if you change your capping, oxide or metal, you will change the whole electric field in your structure. So if you change electric field in your whole structure, what will happen? The Lashba coefficient will change because you have, different effective magnetic field experienced by electrons. So basically, we want to, have a system or some kind of materials which can give us very large effective spin-or angle or large effective SOT fields. So that is our, motivation. So spin-or angle is a material parameter, and this is a theoretical calculation paper. Intensity of spin-or angle as a function of atomic number. You can see there is some kind of linear relationship. So that has, we have to use basically heavy elements because that can give us larger effective spin-or angle. And if you look at carefully, some material will give us a negative spin-or angle. Some material will give us a positive spin-or angle connected with the outermost d electron, shell filling. But luckily, some CMOS compatible materials show large spin-or angle, like tungsten, for example. This is very widely utilized metallization in CMOS that indicate this technology can be incorporated readily in conventional CMOS fabrication process. Then, theorists always give us some guideline. Platinum is what, tungsten is what. It's really true. So we summarize all the experimental report from platinum, and we see a huge diverse report as small as 0.00 something, way up to 0.12. And how come it's possible? It's the same material, but people reported very different values. But once we plot as a function of spin diffusion length and spin-or angle, interestingly, we see inverse scaling. And this indicates basically large resistivity material. Even though it's the same material, if you can tune your grain boundary, annealing condition, or argon pressure during deposition, basically you can change your materials parameter like resistivity. Then large one will give you large effective spin-or angle. So this is kind of a, rule of thumb. And this is due to kind of a spin-dependent scattering. So you inject charge current into your material, then we want to increase the scattering as much as possible. And you have a lot of different types of scattering, like Professor Lee introduced a skew, side jump, and whatever. But once you have more scattering, what will happen? You have also higher possibility to have spin-dependent scattering. Then once you have more spin-dependent scattering, basically you can separate spin up and down in different directions. So that's why large resistivity will give us effectively large spin-or angle. But of course, if you engineer too large resistivity, is it good for application? It's no, because you will have huge power consumption. So always you have to think about some optimization. in terms of effective spin or angle and device power consumption. So then the next question is, okay, now we understand the spin or angle effective value can change depending on material parameter. Then whether the sign is fixed. So we noticed this interesting paper from Masamichi Hayashi group NIMS in 2013. They measured the effective spin or angle or effective field from tantalum, and then larger thickness typically gives a negative value, which is well known and typical. But as you go down thickness below 0.5 nanometer, there is a sign change to positive, value. How come it's possible? It's the same material, just changing thickness. You change sign, and this obviously cannot be understood using conventional spin Hall theory. So we followed this work, and we were able to mimic this from tantalum, and we tried to let's look at the other materials. So this is example of hafnium. So we start from 20 nanometer. We have a typical negative value. This is expected and normal behavior. As we go down, there is a decreasement of value, like a typical spin Hall behavior. Below 1.8 nanometer, we see sign change to a positive value. So this is pretty much the same, like this behavior. As you go down, there is a sign change from negative positive, and you can see negative to positive change. So we naively understood, this behavior, there is a competing phenomena between spin Hall and interfacial spin-orbit coupling. If you make a very thick film, the behavior is dominated by spin Hall. It's a bulk effect dominated. But as you make your film thinner and thinner, then basically your interfacial effect overcome the bulk effect, and somehow interfacial effect has a opposite sign to your spin Hall. Then probably you can change sign in this way. So that is our naive experimental point of view. And recently, as Professor Lee also showed, we also found if you dope your typical copper iron boron platinum bilayer with oxygen, we can also change sign. So that was also strange. But all this experiment tells us basically the role of interface. If you dope oxygen and at this interface, copper iron boron and platinum, somehow we can trigger more interfacial spin-orbit coupling, which has opposite sign to spin Hall. Then you can effectively change the whole structure's value. So recently we tried to mimic or repeat this experiment in one device. So we use gadolinium oxide and the cobalt platinum bilayer. And gadolinium oxide is known to have a huge oxygen reservoir. And by gating, you can push your oxygen into cobalt, and you can pull back, so you can oxidize and you can reduce back and forth depending on the gate voltage. And during this, we also see we can effectively change to positive to negative, positive, negative, spin or angle. So it indeed proved our previous speculation. Once we can dope this interface with oxygen, we can basically effectively switch the spin or angle sign. But this one also gives a kind of interesting perspective in terms of reconfigurable spin logic device, because depending on the gating, you can program in different direction. So that gives an opportunity, not only memory, but we can also think about even some possible spin logic device. So we had a collaboration with Professor Nick in California State. He's a first principle calculation person. So he tried to put oxygen at different layer and see which layer is really responsible for this sign change. And then y-axis is basically Lashba coefficient. And then when we put the oxygen all the way top, and that is corresponding to away from the interface, and we gradually move oxygen in this way, there is some kind of modulation in terms of intensity. But as soon as we put the oxygen at this very first interface, then suddenly the sign changes to a negative value. So this calculation indeed indicate this interface is basically very important to change the sign of this observation. We can also gate our device with kind of different duration and different voltage, and we found it's kind of analog device because the amount of oxygen you can gradually modulate, and depending on the amount of oxidation, we can effectively change the sign from positive number all the way to 0 and even negative, and you can go back and so on. So this is a kind of analog operation, and whenever you see now analog operation, there is another important keyword in our community, that is a neuromorphic device. So we try to use this phenomena and then show some kind of interesting neuromorphic function, and there is spike rate dependence. Depending on how much spike you give to the device, basically you can increase your potential more rapidly. If you slowly give, you can sort of slowly increase your potential. You can also depotentialize. The other one is you can also give a 2 pulse into the device. If those 2 pulses are nearby, basically you have a higher correlation. Then you can also change the potential in large amount of magnitude. If 2 pulses is far away, basically no correlation, and then you have a little effect. So this is called the spike time dependent plasticity, which is sort of an essential feature we have to show if this is some kind of neuromorphic device. So indeed, it shows our device can mimic this synaptic function, mimicking our human synapse. All right, so let me go back to this SOT. So as I mentioned, ferromagnet was the first choice. However, nowadays you see this anti-ferromagnet. This is one of the examples reported by Thomas group using copper manganese arsenide. However, right now they only showed 90-degree rotation. So if you look at by flowing the current, they can change the magnetization from red to blue, black, and black to red. So it's only 90-degree rotation, which is not really compatible with typical MTJ reading scheme. And due to this, they use only the anisotropic magnetic resistance to read out, and AMR value is only a few percent. And the MR percentage is very important for reading operation. If you want to find out what is the information stored in my memory, basically the required time is inversely proportional to the MR value. So in this case, you have to read for a long time. And if you typically look at your memory operation, you have to read very frequently compared to writing. So reading time is actually very important, even though we pay too much attention for writing in scientific research, but reading is actually, in fact, is more important in most of the case. So again, smaller value is not really compatible with real application. So we try to come up with the concept of multi-layer or ferrimagnet in this SOT MRAM. So this is an example of multi-layer. Cobalt palladium is a very well-known magnetic media. People worked on our previous hard disk research. And then luckily we had the tantalum on top. So then we tried to measure effective spin-or angle, and we found enormously large value of 4. And obviously this is very surprising, and typically theorists expect palladium cobalt interface, cobalt palladium interface will cancel out, and then you end up with the first interface. But those are very naive theoretical picture. But if you look at real materials, you always have lattice distortion in this palladium cobalt and cobalt palladium interface. And if you grow multi-layer like 22 times in our case, this strain distortion will accumulate in your whole structure. So basically there is a huge broken symmetry in this multi-layer concept. So we attribute this large effect due to broken symmetry due to strain engineering in this multi-layer concept. The other one I want to introduce is the ferrimagnet. Professor Lee also showed the ferrimagnet can be very interesting in skyrmion or domainal motion, but we utilize this one in spin-orbit torque basically switching. In this case, this material can be easily grown like a bulk PMA, very thick. In this case, we use 6 nanometer, but you can easily grow 20, 30 nanometer, PMA, no problem. And we use a platinum underlayer, and we can study as a function of composition of gadolinium. And we found about 25% of gadolinium is close to antiparallel alignment. in which cobalt gadoliniums are pointing opposite direction. So your magnetic moments are compensating closely. And about 20% gadolinium is close to ferromagnet, and cobalt lattice dominate in this case. So once we measure effective SOT field, we see about 8 times enhancement. In case of the switching experiment, we see the switching efficiency increase about 9 times. So basically, we see about 10 times change in this effective spinor angle once we move from ferromagnet to anti-ferromagnetic coupling regime. And this one we attributed to a negative exchange coupling between cobalt and gadolinium. So if we give a torque to cobalt lattice, basically gadolinium should go, follow to help to maintain the anti-parallel configuration. So this is quite different from the conventional ferromagnet, because ferromagnet you have all the same direction. So if you move some lattice, the other one will pull back actually, in a way. Or later we found this phenomena can be also understood like bulk-like a spin-orbit torque. So in this case we use cobalt terbium multilayer, and then the spin dephasing can be maintained much longer distance due to this oscillating exchange field in case of this ferrimagnetic lattice. So we can have also very large effective spin-orbit torque, about 20 times in this case. All right, so once we have this understanding of quasi-static switching, of course we want to know dynamic property, because in reality all our application is based on short pulse application. Now, so we try to inject short pulses to this conventional tantalum cobalt ion boron device and look at the spin dynamics using picosecond Mach. We give a short pulse like 1 nanosecond with a certain current density. Nothing happened because your energy is not enough to the device. As we move, you can see about 2 nanoseconds, we can have a full switching from top to bottom. And if we increase pulse width more, then initially switch, but then there is a switching back process. So initially it moves from top to bottom, but it switch somewhere in the middle. So once we plot the probability as we increase the pulse width, initially we can achieve almost 100% switching, then it go back to about 50%. And this particular behavior we understand due to domain-wide motion. So when we switch this, the cobalt ion boron, it propagates, then at the end the domain can be reflected. And when you deflect, basically you change your phase. So basically we have to understand this domain-wide dynamics in a lot of materials, because it's not easy to make a single domain due to the PMA nature. PMA material will give you very small domain size, and in realistic device geometry we will always have domain-wide propagation. And now this domain-wide propagation behavior is a bit complex due to DMI, which I am not going to talk about too much detail. So we have to understand those. How much time do I have? 10. I think I should be able to finish. All right, so once we have this domain-wide dynamics, we can also think about how to eliminate the external magnetic field necessary for SOT switching. So we can make this kind of dumbbell structure, and then we can define our domain-wide at a particular position depending on the hysteresis of the magnetic field. Then once you define your domain-wide, we can apply charge current into this device and move this domain-wide back and forth without any magnetic field. This one again because of DMI. And the domain-wide will always stop at this point because the current density in this rounded area is much smaller because of large area. So domain will always stop here if you adjust the amount of current. And you can move back and forth multiple times. You test it a million times, it never disappears. But like a typical racetrack memory, if you have a multiple domain-wide and you move, there is some interaction and it's not easy to maintain. But in case of a single domain-wide, we found it's much easier. Right, so then we can easily integrate those with the conventional MTJ on top, and you can read out. And due to this, we have some energy saving because we don't need to nucleate the domain-wide. We already predefined So we can also move at zero current. Time to wrap up. 5 minutes. So as I mentioned, this topological material is also very interesting in the community because of spin momentum locking. So depending on the electron direction, the supported spin is in a right angle, very particular. So people think we should have a giant spin or angle. Of course, many experimental group report a wide range of value, effective spin or angle, as small as 10 to minus 4, all the way to 425. So you can see somebody is doing wrong measurement. But if you again plot as a function of Ti thickness, we have very interesting inverse scaling. So once you have, it's relatively easy to understand. This material we call insulator, topological insulator, but it's not. It's a very dirty semiconductor. Okay? And due to the cellular vacancy during the material preparation. And where's the Fermi level? Fermi level is supposed to be somewhere in the middle of the gap, but in reality, we have Fermi level all the way up to conduction band. So when you inject charge current, what happens? A lot of current are shunted through the bulk due to this band. And if you have, bulk band, there is no such a spin momentum locking property. Right? So forget about this interesting effect. It only happens at the surface. So that's why once you use a very thick film, your spin efficiency will be negligibly small. But if you reduce your Ti film less than 10 nanometer, we start to see huge effect. But of course then, maybe we should use a very, very thin film. The problem is again, your effective spin or angle is large, but your resistivity again, very large. If you have a very large resistivity, your power consumption will be enormous. So it's not advantageous. So we have to choose somewhere, here for device application. So we choose about 8 nanometer, and then we put nickel ion on top. Then this is top view using MOC microscope, and we can look at the domain where propagation and switching, which apply charge current. All black domain indicate initially in this direction. We can switch back, and then also applying charge current from opposite electrode, we can switch to the initial configuration. The switching current density is very low. It's a 6 times to 10 to 5th ampere per square centimeter, typically 1 to 2 orders smaller compared to that of heavy metal. This happens without any magnetic field at room temperature. So indeed, topological insulator, can be used in probably, possibly some application. And recently, people try to even deposit this material using sputtering. So if you look at the report by Professor Jinping Wang from Minnesota, they use the sputtering process, and they reported also very large efficiency. So I think it's kind of interesting. The next question would be, if you have a sputtering and no, crystalline structure, whether you can talk about topological, density of state. So I think that is quite an interesting aspect we have to think about. Perhaps it's just all because of very high spin-orbit coupling coming from the material. It's probably nothing to do with the topological band. So last few minutes, I just want to introduce a new sort of area called, terahertz, what we can offer even, spintronics. Traditionally, it's not easy to access because it's in the middle of microwave and the optical band. Even though a lot of interesting applications were proposed, like a safety surveillance due to smaller wavelengths. After packaging, you can even inspect the IC chip because terahertz can penetrate the plastic packaging. Even some doctors want to use for their medical treatment and so on. But however, I find the most exciting application is detecting black hole using terahertz. So like 2 months ago, probably you heard the news media talking about human being finally measured this immediate black hole using 0.23 terahertz. This is the frequency, can penetrate all the galaxies. And they use like a 6-7, microscope at the same time. Anyhow, it's very interesting. And the bottleneck is basically there is no real good, room temperature affordable, reliable terahertz emitter. That was the problem. So we noticed this interesting paper by Tobias Kampras's group in 2013. So they use a cobalt gold bilayer. If you shine femtosecond laser in this bilayer structure, you can generate terahertz. The operation principle as follows. If you shine laser to magnetic material, your magnetic material absorb energy and local temperature increase crazily. During the cool down process, you have spin up and down, diffuse in different velocity. Okay, so if you measure now coming current from the perspective of this heavy metal, you see spin imbalance due to the different diffusion velocity. So that can be considered as a pure spin current. Once you have a pure spin current coming into heavy metal, then you have this inverse spin Hall effect that can convert into charge current, and this charge current oscillate in a frequency of terahertz. So it can emit terahertz. So it's a kind of a non-linear frequency conversion process from hundreds of terahertz to a few terahertz. And typically this non-linear process has very small efficiency. Okay? And this one also doesn't have that high efficiency, but that is true for all these non-linear frequency conversion process. So my students so much excited and came to me. He spent enormous time for materials, understanding interfacial optimization. Then he found 6 nanometer tungsten, 3 nanometer cobalt on top of glass. Substrate is very important, not to absorb terahertz, can give a very high power emission. And we compare with the commercialized zinc telluride crystal. This is a quite expensive gem. Half millimeter thick. You can see the power output is almost same as our thin film 9 nanometer, sputter prepared, device. And he was so much excited about this opportunity and started the company. So he put all kind of a terahertz component into a small form factor and use fiber-based femtosecond laser. Nowadays, you can buy a very small iPhone-size femtosecond laser. Operated by fiber optics. Then we can put our terahertz emitter and made a complete terahertz spectroscopy system. And this can be, used for some molecular vibration detection, some thickness measurement, or chemical composition analysis, or even maybe black hole detection, probably. But you have to have probably a lot of those to measure black hole. So as a quick summary, I showed you, what we can do in terms of technological aspect using this interesting spin orbit, phenomenon. A lot of materials aspect, should be understood. Oxygen content, resistivity, and even this oxygen motion, can be applicable to neuromorphic or spin logic devices. Structural symmetry breaking, multi-layer concept, those can be also applicable to skyrmion. And strain engineering is something we should pay attention. If you look at, conventional CPU, P-type transistors mobility is engineered by strain engineering. If you look at our laser diode, most of the density of state is modified by strain. Okay, so strain engineering, used to be a key ingredient in, I think, modern electronics and optics, and probably now we have to apply this one in our spintronic devices. As some alternative, I think ferromagnet is somewhere in between, ferromagnet and anti-ferromagnet. It's easy to fabricate, it's relatively easy to measure, and if you look at like 20 years ago, magneto-optical disc, was commercialized. Okay, that precisely used the cobalt gadolinium compound. So I don't think, the materials is a bottleneck. This material was commercialized and it's time to revisit in spin orbital business. And some topological, materials are interesting, and scientifically we should investigate. And nowadays, people even expand to wire or even the two-dimensional electron gas. And finally, using exactly the same structure, but using inverse physical process, we can convert now from spin to charge, and we can generate even terahertz emission. So for this, I want to thank many of my group members who contributed the data I present today, and as well as many international collaborators. Okay, thank you very much.
Question. Thank you, Professor. I have a small question. Just now, you mentioned that topological insulator has a very large spin Hall angle, but due to the large resistance difference between the Ti and the ferromagnetic layer, when you inject a current into the system, there will be a thermal gradient along the z direction. So there will be some thermal effects such as Nernst effect or anomalous Nernst effect. So when you obtain your spin Hall angle, have you considered such thermal effects?
Sure. So thermal effect always it doesn't really depending on the current direction, because your thermal effect in the g direction will be same. Either you apply current in this way, this way. So you can always subtract your thermal effect by doing this current direction dependent measurement, and the final output should be purely current direction dependent effect. So you can always subtract those. And in fact, in our measurement, we found the current thermal effect is negligible in terms of switching contribution. But in all switching measurement, actually, due to the thermal effect, you reduce your magnetic sort of anisotropy. So that should be considered always. It's impossible to avoid. So that's why if you do the switching measurement from DC regime, basically your switching current is always lower because of heating effect. If you now reduce your pulse width, basically the required current increase, okay, and then increase crazily. So basically this regime, the quasi DC regime, is basically thermally induced switching regime. And then if you shorten your pulse width, you can go more pure dynamics regime coming from your magnetic.
Oh, thanks.
Thank you very much for the nice talk. In a fixed ferromagnetic heavy metal bilayer, if the capping layer, oxide capping layer is changed, like MgO or SiO2 or ALO, so due to Rashba effect, we could expect different spin Hall angles for that particular fixed heavy metal ferromagnetic bilayer.
That's right. Yeah, I think that is expected. And then I noticed a paper from Professor Kang Wang group in UCLA. So they use the different capping materials, different oxide or nitride. I think they also showed quite different values.
Thank you.
But I think the understanding is lacking. I think we should look into more details, more systematic study, and even you can put, not only oxide and nitride, you can also put metal. Different metal will give you also different work function and so on.
Okay, thank you.
Thank you for your talk. Could you quickly give an insight in the concept of the spin Hall angle? Because I thought the spin Hall angle to be somehow a measurement of the efficiency, how you can convert electrical current to spin current. But therefore, I thought it was like a maximum value there, like 1, so you cannot convert too much. And now we've seen values over 1. So there, I obviously have a misconception of the spin Hall angle.
Well, you can consider as a conductivity concept. For example, as I defined, is spin conductivity divided by charge conductivity. So when you look at, in a material system, I measure longitudinal or transverse conductivity. My conductivity in transverse direction can be larger than the longitudinal direction. Then why not the value can be more than 1? But if you define as a current, that is the problem, because your current should be sort of conserved quantity. So you imagine, oh, I injected 10 electrons. Then you want to count how many in the lateral and the transverse direction. Then you have, I think, the problem.
Thank you very much.
Okay, so this is the end of morning session. So we'll break for lunch now, and we'll be back here at